We have been discussing digital modulation techniques for some classes. We have so far discussed PAM, PPM, PSK, QAM, FSK, all these modulation techniques, and we have also discussed what is an orthogonal signal set. We have seen that FSK, PPM signal sets are orthogonal. We have also discussed what is a biorthogonal signal set, and we can get a biorthogonal signal set also from FSK, PPM signal set, but also including their negative signals. Then in the last class we have discussed receiver structures, how to demodulate for a given signal set. So, we have seen that if we are given a set of signals that are being used by the transmitter, how to do the reception, how to do the demodulation at the receiver. We have not assumed any particular type of modulation there. We have assumed that the signal set that is being used is known to us, but it is not decided by us. We have seen how to demodulate for the signal set, and there we have discussed, we have seen that using this block diagram by computing correlation, first by multiplying by the correlation with the basis signals, by multiplying and then integrating, we can find the correlation of the received signal with the basis signals, and then we can find the correlation of this vector with different signal vectors x m by performing this operation for each m. Then by adding this, we have seen that these are, here we will get the quantities which we wanted to compare to decide on m. So, here the output is this correlation plus minus mod x naught square by 2 and so on, and then we select the maximum of them, that will give us an estimate of m. So, which one is maximum, that number m will be the estimate at the receiver. So, we can get the message, estimate of the message this way. We have also seen that these blocks, this block and this block, all these blocks can be implemented using matched filters matched to the basis signals, like this. Using a matched filter and the sampler, we can again get these quantities, and then we can do the same operations here. So, this is matched filter receiver where the same operation is done using matched filters. Then we have also seen that using matched filters we can also demodulate differently by using matched filters matched directly to the signal set instead of the basis signals. So, here we have seen that we can use these matched filters matched to the signal set, different signals, and then sampling we will get. Now, we can compare directly this. So, we have also derived and shown that this will do the same operation as we wanted to do using a correlation receiver or matched filter receiver, using matched filters matched to basis signals. So, now we will see that we will see in particular what will be the receiver structure for different kind of modulations. So, first of all, for PAM, QAM signals, we can, the dimension is either 1 or 2. For PAM it is 1, for QAM it is 2. So, for PAM we will simply need, it is one dimensional, so we will need only one matched filter, and then we will find in which section the received the point lies. Then for QAM again we will need two matched filters because we have dimension 2. Number of points may be 16, 64, 32, anything. So, having matched filters matched to all the signals will be too much complexity at the receiver, because then we will need 64 matched filters, 32 matched filters. So, for that reason it is better to implement the matched filter receiver structure in this form, matched to the basis signals for QAM here. So then we will need only 2 matched filters. Now, for PSK again the dimension is 2. So, we can use the same matched filter structure with 2 basis signals, and then here instead of doing this correlation and then finding this, for PSK signal particularly we can do it in a slightly different way and easier way. So, for PSK we have this transmitted signal set. Suppose 8 PSK. Now, when the noise corrupts this signal, if we transmit for example this, we will receive somewhere here, one of these points probably nearby. If the noise is too much at that point of time, then it may go to near here also, then we will decode wrongly because it will come nearer to another point. But anyway, we cannot do anything about that because we cannot remove the noise completely. So, what we need to find out is to select the nearest point in the constellation. Suppose you have received this, we want to choose this. So, how do we select? As we said, we can compute the distance and then we can show that comparing the distance and picking the minimum is equivalent to finding the correlation with each and then adding something and then comparing those values and then taking the largest. We have seen that here. We are selecting the largest. Actually, it is equivalent to comparing the distance from each point in the constellation. So, instead of even doing that, instead of taking the distance or instead of taking the correlation and then equivalently finding the distance and comparing, we can simply find the phase of this point and see which is the nearest point here in terms of phase, meaning by if the phase of this here is this, then this phase is nearest to which phase of which signal here, which point here, that we have to see. So, if we receive y equal to y naught, y1, a point here is y naught, y1, we can compute the phase theta y or angle y by taking tan inverse y1 by y naught, and then we can find in which interval it lies. If the phase is in this range, it is this point, because then all these points, this is the nearest point. For all these points in this interval, this is the nearest point. So, it depends on the phase of the signal. If the phase of the signal is in this range, then it is this point. If the phase of the signal is in this range, then this is the nearest point, and so on. If the phase of the signal is in this range, then this is the nearest point, and phase of the signal is in this range, then it is in this, this is the nearest point. So, this phase now we can compare in which range it falls, whether it falls in this, whether it falls in this, and so on. So, here we will see that the phase of this is in between this. So, we will know that this is the one which was transmitted. Now, these regions are called the decision regions. So, for PSK we have these points. Then if the received point is in this region, then we will decide in favor of this point. We will decide that this is the one which was transmitted. So, this region is called the decision region of this point. Similarly, for this point, this region is called the decision region of this point. So, by finding the phase and then comparing this phase with these decision regions, a phase of this, we can find out which point is nearest. So, this is simpler than finding the correlation and all. just find the phase and see in which region it falls. Okay. So, talking about decision regions, what are the shapes of decision regions for example, QAM? So, if you have 16 QAM constellation, what is the decision region? What are the decision regions? This is the 16 QAM constellation. What is the decision region for this? This is the decision region. We can see that if the receipt point is in this region, then this point is the nearest to that point. This is further from here, so this is nearest. Even if it is here, this is the nearest point. So, all these points are nearest to this. Okay. Similarly, decision region of this point is this infinite region. Decision region of this point is this infinite region. So, there are three kinds of shapes of decision regions for 16 QAM. One is square closed, one is semi-infinite in one direction. Here it is semi-infinite in both directions. So, now for PSK we have seen that this can be done this way, finding the phase. Now, if we take the FSK or PPM modulation, now we know that, so we are considering now FSK or PPM or any orthogonal signal set. So, for any orthogonal signal set like FSK and PPM, we know that the number of points is same as the number of same as the dimension of the signal space. So, for that particular case, we can say that these two receiver structures are of approximately same complexity. See, here also we will need n number of, so for orthogonal signal set m is equal to n. So, here and here we will require the same number of matched filters. But here we need to do all this, but here we will see that this xmj will be will be non-zero only for one particular j. So, as a result, this is a very simple operation. So, we can say equivalently that this itself, this structure itself will do for FSK. This itself is of the best complexity. Just take the matched filters matched to each signal, because they are orthogonal, they are the basis of the signal space anyway. So, find the components in each direction along each signal, orthogonal signal, and then this also need not be done now, because for FSK and PPM or for any orthogonal modulation technique, we have discussed that the energy of each signal is same, is E. So, this x naught, mod x naught square is same as mod x1 square and so on. So, they are all same. We are adding the same quantity to each and then comparing. So, this need not be done. Whichever is largest here will be here also, this one will be largest among these, because we are adding the same quantity to all of them, because all these are same. So, for FSK we can say that we can simply take this, but we need not have these additions. So, it is a simpler structure. Now, how do we verify that it will be really nearest to that? Suppose this is largest. Can you say that this will be the nearest? Yes, we can, because we have proved that this actually does the optimum, and this is equivalent to finding the nearest point in terms of the distance. So, if you just choose the largest here, this will give us the minimum distance point. This will tell us which signal is the nearest to the received signal. Okay. So, for FSK, we have concluded that we can detect this way, that first find this vector that is this vector, this is y naught, y 1 and so on, and then take the component which is largest, choose take y take the m maximum of yi, take the argument of that argmax. This is our estimate of m. What does this mean? This means that this is the argument of the maximum yi. So, take which one is the maximum, what is the argument of that. If y 4 is the maximum of all these, then 4 is the argument of that y 4. So, that 4 is the m hat. So, this is our estimate of the message that was transmitted. Okay. So, this is quite simple. This is simpler than finding out the inner product and all such things, because those actually will result in having the same result. We will get the same result using that. Okay. Now, we leave it. I leave it as an exercise for you to find out what will be the detection scheme for bi-orthogonal signal. So, we will discuss it later, but please give it a try and then we will discuss it later. So, we have seen the receiver structure in general for any arbitrary signal set, and we have also discussed some special cases of signal sets and what will be the receiver structure, simpler receiver structure for that kind of modulation techniques. Now, we will discuss another kind of signal set which is also important and interesting, but before doing that we need to discuss some general aspects of signal design. So, one is that this we will discuss now about equivalence of signal sets. So, if you are given two signal sets, sometimes two signal sets may be equivalent in terms of probability of error or in terms of the performance of the signal set, in terms of how much reliability it gives in the communication. So, if both the signal sets give us same probability of error, but one signal set, for example, suppose if it gives it uses less energy, then obviously we would like to take that signal set, because we would be transmitting less energy to get the same probability of error using probably the same bandwidth. So, whenever possible we would like to get the same probability of error with the minimum energy required. So, in that context we need to find out when two signal sets are equivalent. So, we will not find in general when two signal sets are equivalent, but we will discuss some types of transformations which keep the signal sets equivalent. So, if we have one signal set and we do some transformation on that, will that signal set remain equivalent to the original signal set? So, there are some kind of transformations which keep the signal set equivalent to the original signal set. So, one of them is translation. So, suppose you have a QAM constellation like this. Suppose the amplitudes we use are these 3 points, or let us say we have 4 points. You are using transmitting 2 bits using this signal set. So, this basis may be sin omega ct, this may be cos omega ct scaled by something. But now we can see that this signal set can be easily brought here. By translating each point by the same number, we can bring this point to 0, and then this signal set would look like this. Signal set will look like this, and now this the center is here. So, we can intuitively feel that the energy of each signal is reduced here. We can see that because they are brought nearer to 0. So, as a result, the average energy transmitted using this signal set will be less than average energy that is used to transmit this signal set. So, this we can feel also that this performance of the signal set here and here will be same. How do we see that? You can see that if this signal is transmitted here and it is corrupted by noise, it will go here. So, probability that the noise is so much that it will bring the point to nearer to other points, that will be same as if this is the noise deviates from here, brings this point here, the same noise will deviate this point to here. So, if this comes near this will also point will come here for the same noise. So, probability of error here will be same as probability of error here. Now, we will also see in a different way how to fill this. So, for that, let us suppose that this is the signal set we are using, x naught, x1, xm minus 1, and suppose we have a. This is any vector in the same signal space. So, these are the vectors, vector representation of the signals that are transmitted. So, meaning by we have taken an orthonormal basis of the span of the signal space, and then with respect to that orthonormal basis we have expressed each signal as a vector of n dimension. So, these are those vectors. Then we are taking another vector in the same signal space, and then suppose we construct this signal set, we take x naught minus a. Now, what is this? This vector, suppose x naught is this and a is this. What is x naught minus a? It is this. That means, from origin if we draw, it is this. So, we are basically subtracting a from this, means we are bringing the point here in the negative direction, negative of a. So, if we add, this point will go here. This is x. If this is x naught, this is x naught plus a. So, we can shift it in this direction. We can take a here, a to be this vector, then this will come here like this. So, by adding a vector, adding a suitable vector, we can shift a point to anywhere we want. So, now we take a single vector and shift all the points by that same vector. So, all the points will be shifted in the same direction parallelly. So, those new points will be x naught plus a, x1 plus a, and so on till xm minus 1 plus a. Okay. Now, our claim is that if we use this signal set, which is the shifted version, translated version of the original signal set, it will result in the same probability of error as the original signal set S. How do we see that? Suppose we are transmitting this signal set, the transmitter is using this signal set, and receiver has received yt, and it has also extracted using matched filter or correlation receiver, it has extracted the vector y. This is also same as x m that was transmitted plus the vector n. So, this is what it has received after match filtering. So, now this xm is this xm, let us say we are using this. So, we are not, it will not receive xm, but xm plus. If we transmitted this, noise will be xm plus a. If we transmitted, noise will be added to that. So, we will receive here xm plus a, then plus n. This is the transmitted vector and this is the noise. So, this is the noise and this is transmitted. So, we have received this. Now, what can the receiver know? Receiver do? Receiver knows this vector a, because this is a fixed vector, and it can simply subtract a from y. It can subtract a from y and then get xm plus n. So, if we transmit this signal set, and if we then receive this, that is this plus noise, then we can simply subtract A at the receiver from the received vector, and then we can assume as if this signal set itself was used by the transmitter and we have received this. So, this is, see, it is the same situation as if we transmitted this. So, only thing we need to do is just subtract A, and then we can decode, we can do the demodulation just similarly as we would have done here. So, we will have the same structure to do this. Here we have received these y's, which are these. So, before comparing, what we will do is we will just subtract from each this A, and then we will go ahead with the same thing, assuming that these x, m, j's and all are same. So, we have basically used this signal set, we will assume. So, the receiver can do the reception, do the demodulation exactly similarly with just a minor modification, and the performance will be also same, because here the same noise is being added. So, it is as if this itself was transmitted and this noise is added. So, we will have the same probability of error. Okay. So, we have discussed that the translation keeps a signal set equivalent, meaning by in terms of probability of error, the probability of error remains same even if you translate a signal set. Now, this is not the only transformation which keeps a signal set equivalent. Rotation also keeps a signal set equivalent. Suppose that we have rotation in higher dimension also can be defined, but we will not go into that, we will just discuss in 2 dimensions. Suppose we have, say, if we have these 4 points, we are probably using this, then if you rotate this set of points around any point, then also the signal set will remain equivalent. Why? Suppose we are rotating the whole set of points around this point, we are rotating the whole set. Then at the receiver, what can we do? We can rotate it back to this position. We will receive some vector, suppose we transmit this, so we will rotate it, we will get it some vectors here. So some points we will have here once we rotate it, and then if we transmit this, we will rotate, we will receive something here, and then we will rotate it back here, so we will get something here, and then we will decode. So rotation will not also affect the probability of error. Detection also can be done very similar to detection of this signal set, and the probability of error also will not change. Okay. So we have seen that translation and rotation do not change the performance of the signal set, that is probability of error of the signal set, and as a result we say that the signal set remains equivalent after translation or rotation. So let us now see some interesting consequence of this concept. Suppose we are given a binary signal set, so 2 points. If it is 1, it transmits this, if it is 0, it transmits this. Now someone uses this signal set. I can say that I will not use this signal set, I will instead translate it and then rotate it appropriately so that the signals are here. So I will rotate the signal set around this point, the midpoint here, and to make it horizontal, and then shift it to bring this point here. So it will first go to horizontal location, then we will translate this way. So we will bring the points here. Then it is same as doing PIM. So instead of doing this, why not I do this? This is a PIM modulation. We are familiar with this, we know how to demodulate, it is very simple. So we see that if we are given any 2 points in the constellation we want to transmit, we can also equivalently transmit the translated and rotated version of the signal set. Okay. So similarly, if we say use binary FSK, so orthogonal FSK, it will be like this. So I can say this is also equivalent to translating and rotating to bring it to this type. So performance wise, reliability or probability of error wise, this signal set will be same as this, but this will probably use more bandwidth. This dimension 2, this is dimension 1, and decoding complexity is something we have to again see. For probably these things will not matter for small number of points, but suppose now we take, this is 2 dimension, now take 3 dimensional FSK. Take 3 dimensional FSK. Now by translating and rotating, we can now bring this in 2 dimension. So this is 3 dimension. We can translate the signal set and rotate, so that the midpoint of the, if you join these 3 points, there will be a plane, and there will be a triangle on that plane joining these 3 points. Take the midpoint of that, and then centroid of that, and then bring that centroid to 0 and rotate the plane so that it lies on the xy plane only. So then we will get a signal set like this. So it is also equivalent to a 2-dimensional signal set. 3-dimensional FSK orthogonal signal set is equivalent to a 2-dimensional signal set with 3 points. This kind of signal set is called the simplex signal set. Now, how do we know how much translation is required? So that we will see. We know that given a signal set, we can translate it to anywhere, and it will the probability of error will not change for that region because of translation. So now, but different translated versions will have different average energy. So we would like to choose that particular translated version which has the minimum average energy. We don't want to transmit more power. So we have to find out of all the translated versions which is the minimum energy version. So suppose we have this signal set x0, xm minus 1, and suppose the centroid of these points is, so we call it x bar. Centroid is nothing but average of all of them. So this. Now take any vector a and translate this whole signal set by minus a or a. So what do we get? We call it, this is S, the original signal set, and this translated version we call SA, S subscript a. This is defined as x naught minus a xm minus 1 minus a. This is the signal set we are using, suppose. Now we know that these two signal sets are equivalent in the sense that they will give us the same probability of error, and this can be receiver for this can be implemented in terms of the receiver for this, just with a minor modification. Now we will compare the energy of these two. So what is the average energy of this signal set? The E average of this signal set SA is the 1 by m summation energy of each, I equal to 0 to m minus 1 xi minus a square. Now this we will do a little modification. We will subtract here xi minus x bar, then plus x bar minus a whole square. Now, what is this? We know that length square, this is basically energy, but energy is in terms of vector, the energy is the length of the vector square, and that is same as the inner product of the vector with itself. So, we take the inner product of this with itself. So, what is it? It is 1 by m, and then inner product of this with itself we can break now into parts, this times inner product of this with this and so on. So, we will have this with itself will be again energy of this. We take the summations also we break, then the energy of this, then the inner product of this with this, and then inner product of this with this. So, that is the same thing. So, we will have, we are considering real vectors. So, we will have 2 times that. So, we will have plus 2 times this is xi minus x. Now, this also summation over, this summation will come here also. Now, this summation, so this is 1 by m. Now, this can be written as, this one is nothing but the average energy of this signal set, this signal set. So, we have average energy of S, not average energy of S, not this signal set, but this is the signal set, the translated version of this by x bar. So, in place of A, if we put x bar, we will get this signal set with A replaced by x bar, and then an average energy of that will be this, So, this is S x bar, translated of S translated by x bar, average energy of this is this. Then we have this quantity, and then plus we have this quantity. Now, let us see what is this quantity. 2, the only term dependent on I is this term. So, we can take this summation only here. So, we have x bar minus a. Then what do we have here? Average of all these for all i's. So, that is nothing but this. So, that is x bar. So, we have here, from here this summation you take here 1 by m summation here, we get x bar, minus we have x bar again. So, this is 0. So, this is greater than equal to, you can see that this quantity is always positive, non-negative, 0 or positive. It is greater than equal to E average S x bar. So, we can say that among all the translated versions, this is the minimum that can be achieved, and this is equality only when x is equal to a bar, because only then this will be 0. So, the average energy will be this. So, S x bar has the minimum energy, average energy among all the translated versions of x, of S. So, we conclude that Sx, this translated version, has the minimum average energy. So, we have seen that if you translate a signal set by any vector, the probability of error does not change, but the average energy changes, and among all the translated versions of a signal set, the one which is translated such that the average of the signals, that is the centroid of the signals, is the origin. When we translate such that the centroid comes to 0, then that has the minimum average energy. So, now we will see an example of that. We have just now seen, before discussing this, we have seen that if you have an orthogonal signal of dimension 2, we can bring it to, by translation and rotation, we can bring it to a signal on one dimension. Similarly, 3-dimensional orthogonal signal set can be brought by translation to a 2-dimensional signal set. So, now we will generalize that concept, and that kind of signal set is called the simplex signal. Simplex signal set. So, what we do is simple. Suppose we have this is an orthogonal signal set. Then, just like we did for the 2-dimensional and 3-dimensional orthogonal signal set, we will do the same thing here. In general, we will first find out the average of all these, that is the centroid of all these signals. So, this is 1 by m. And then we will basically construct another signal set, that is the translated signal set, where we will subtract this average from each. So, that is, let us call that W m t, that is x m t minus x bar t. That is, now in terms of vector, we can say that the vector representation of this will be W m, that will be x m minus x bar. These are the vector representation of these signals with respect to some orthonormal basis. Where x bar, because x t is this, if you represent in terms of vector, vector of this will be again this linear combination of the vectors of this. So, x bar is 1 by m m. So, what have we done in terms of constellation? Just like we did for 2-dimensional and 3-dimensional signal sets, we have taken first the average of all these signals. So, that we have computed the centroid. Now, we are subtracting the centroid from each to get a new signal set. So, now this signal set will have centroid 0, because we have brought the centroid to 0. So, if we had some signals here, we will compute the centroid and then bring it to 0. So, we will take this vector, we will shift it to by this vector. We have done that. Now, we will see its properties, the properties of this signal set. First of all, we claim that the energy of the signal, each signal still remains same. Orthogonal signal set also had energy of each signal same, E. But now, we will see that all the signals still have the same energy. So, let us see energy of W m. What is W m? W m we have just now seen is x m minus x bar, and then we take the energy of this. Now, this is nothing but the inner product of this with itself. So, we take inner product of x m minus x with itself, and This we can again now do distribution, distributivity, use distributivity and use inner product of xm with xm. So, that will be mod xm square energy of xm, then x with x, then minus xm x minus x xm. Both of these are same because we are considering real vectors. And what is this inner product? This inner product, this magnitude is xm, we have taken of energy E. The orthogonal original orthogonal signal set, we have assumed that to have energy E. So, this is E. Now, what is the energy of x bar? Let us see what is x bar. X bar is this. So, what is the energy of this? It is just the E by m, because energy of this is nothing but inner product of this with itself, and when we do that, do the inner product, we can do distribution. We can do distribution like this. So, if we have x 1 by m x naught x m minus 1 with 1 by m x naught plus x m minus 1. If we take this inner product, 1 by m square will come, and then inner product of each combination x naught, x naught, x naught, x1, all these inner products we have to take. But this signal set was orthogonal. So, inner product of x naught with x1 will be 0, x naught with x2 will be 0, and so on. So, we will have only x naught with x naught, x1 with x naught, and those only those inner products. So, we will have from I equal to 0 to m minus 1 inner product of xi with xi itself. All the cross inner products will be 0. So, this inner product we know, this is the energy of xi. So, it is E. So, 1 by m square, there are m number of them. So, m times E. So, this is E by m. So, we have this inner product, this as E by m. Now, what is this? Is 2 times this, these two are same. So, minus 2 times xm with x bar. Now, if you take xm with x bar inner product, x bar is this, you take a particular xm and take inner product, xm with all the other components other than m, those inner products will be 0. Only for m it will be E, inner product of xm with xm itself is energy of it. So, E, then E by m. So, we will have this inner product as E by m. So, this is E plus E by m minus 2 E by m. So, E minus E by m. This is nothing but 1 minus 1 by m. Now, this, as you can see, this is less than E. This is something interesting. It shows that all the signal points in the simplex signal set are same, but they are less than the energy of the orthogonal signal set, which was E. And for the simplex signal set, the energy of each point is, each signal is E times 1 minus 1 by m. So, the energy of each signal has reduced, but the distance between the points remains same, because all the points are translated by the same vector. So, the distance between them has not changed, and we have also discussed before that the probability of error does not change at all. So, we have seen that energy of the simplex signal set is less than the original orthogonal signal set, though the probability of error for both signal sets are same. Now, second, what is the inner product of x, y, the two signals in the simplex signal set? For orthogonal signal set it was 0, but now they will not be orthogonal, and we can compute this and this, once you compute, you will see that this is minus 1 by m, and it is independent of m and n. So, it is also constant. this is constant, and so all the any pair of signals from the signal set, simplex signal set, have the has the same inner product, that is correlation, and also distance between any two points remain same. Distance between Wm and Wn is same as distance between xm and xn, because we have translated both the points by the same vector. They have come to a different location parallelly. So, the distance between the pairs of points have not changed when we translated the whole orthogonal signal set to bring its centroid to 0. So, we have discussed in this class that by translation and rotation of a signal set, the probability of error does not change, and as a result the signal sets are called said to be equivalent. They have the same performance in every aspect except for average energy transmitted, which changes when translation is or rotation is done. So, using this principle, we have seen how to bring an orthogonal signal set to centroid 0 and thereby reduce its average transmitted energy. Among all the translated versions, that will give the minimum average energy of the signal set. So, that signal set, when we obtain from orthogonal signal set, is called the simplex signal set. From the next class onwards, we have finished this memory-less modulation techniques. Next class we will discuss modulation techniques with memory. Thank you.